Good morning to one and all. I'm Soumya from Government Women's College, Kolar. The paper 501 consists of statistical physics, quantum mechanics, and atmospheric physics, and nanomaterials. This lecture is useful for the final year BSc Physics students. The unit 1 consists of statistical physics, and the session 1 is on basic concepts of statistical. Statistical mechanics deals with the system of large number of particles and overall behavior of the system related to the particle themselves. The statistical mechanics is not concerned with the actual motions or interactions of individual particles, but instead with what most likely to happen. There are two types of system, the microscopic system and the macroscopic system. A system of atomic dimension or of smaller size is called microscopic system. The systems are large compared to atomic or molecular dimension. They are therefore called macroscopic systems. The examples for the microscopic system are molecules, atoms, electrons, photons, etc. The examples for the macroscopic system are solids, liquids, gases, electromagnetic radiations, and so on. Again, the state of the system is of two types. One is microstate and the other one is macrostate. The microstate is defined as the distinct arrangement of each molecule or atom in the system at a single state. The macrostate is defined as it is the distribution of particles of a system without distinguishing the particles among themselves is called Stirling's approximation. For a large value of n, the calculation of n factorial becomes very tedious. So hence the Stirling's formula gives an approximate value of n factorial. So the proof for the n factorial, so let us consider we have a n factorial. The expansion of the n factorial is done by 1 into 2 into 3 into 4 up to n. Again, if we take a ln for the n factorial, the expression can be written as ln n factorial is equal to ln 1 plus ln 2 plus ln 3 and so on. And ln n to the power of n, the expansion of ln n to the power of n is, it is ln n plus ln n plus ln n and so on. If we divide the expression 1 divided by 2, the ln n factorial divided by n to the power of n can be written as it is ln 1 divided by n plus ln 2 divided by n plus ln x divided by n up to ln n divided by n. So if we take a summation for this, the value of x runs from 1 to n, it is ln x minus ln n. Replacing the summation by ln n factorial divided by n to the power of n can be written as it is integration x runs from 1 to n ln x minus ln n dx. So by this integration is done by making use of integration by parts method and also by applying a limits for the same. So we get the expression as it is ln n minus n plus 1. Again, the function ln n factorial divided by n to the power of n is of the form of log a by b, which can be written as log a minus log b. On further simplification, so we get the final expression for ln n factorial as n ln n minus 1, and also by neglecting the higher order terms. The final expression is of the order of is the form of ln n factorial, which is equal to n ln n minus 1. A priori probability. So here the a priori probability is defined as it is a ratio of area of the ith cell divided by total area of the. Hence, a priori probability of distribution of n balls among the k cells so that n1, n2, n3 up to nk balls falling in the corresponding cells can be written as g1 to the power of n1, g2 to the power of n2, g3 to the power of n3 and so on up to gk to the power of nk. The value of I runs from 1 to k. If we take a summation for all, so it is summation I runs from 1 to k gi to the power of ni. The next is the thermodynamic probability. Let us consider we have n distinguishable balls in a box having k compartments such that n1, n2, n3 up to nk are the number of balls in the compartments 1, 2, 3 respectively. So let us consider we have a n1 balls which are to be distributed in the first cell. So this can be done in the number of ways, that is n(c)(n)(1) ways. So n(c)(n)(1) is equal to, it is n factorial divided by n1 factorial into n minus n1 factorial. So these are the number of ways in which by which the n1 balls can be distributed in the first cell. So the remaining number of balls which are present in the system are, it is n minus n1. N is the total number of balls which is present, and then minus n1, already n1 ball has been occupied in the first cell. So hence the remaining balls which is left is n minus n1. So now the n minus n1 c n2 is equal to, it is n minus n1 factorial divided by n2 factorial into n minus n1 minus n2 factorial. So these are the values which is remained in the second cell. So hence n minus n1 factorial divided by n2 factorial, n minus n1 minus n2 factorial. So this is the value or the number in which, the number of ways in which the second particle can be occupied in the second cell. Similarly, if the n particles should be of the number of cells, then the thermodynamic probability can be written as n factorial divided by n1 factorial, n minus n1 factorial into n minus n1 factorial divided by n2 factorial into n minus n1 minus n2 factorial, and so on. If we take a summation of all this, the value of n factorial, it is n factorial divided by n1 factorial, n2 factorial up to nk factorial, and then again the expression in terms of summation can be written as n factorial divided by summation I runs from 1 to k ni. Again, the probability of possible distribution W is equal to, it is the product of a priori probability and thermodynamic probability. So hence W is equal to, it is G into omega, where the value of this can be written as summation I runs from 1 to k gi to the power of ni into n factorial divided by pi, or the summation I runs from 1 to k ni. So this is called as total thermodynamic distribution. Again, the expression can be written as summation W is equal to, it is summation n factorial divided by n1 factorial, n2 factorial up to nk factorial. Again, it is g1 to the power of n1, g2 to the power of n2 into g3 to the power of n3, and so on. Again, if we take a summation for all these terms, again the expression can be written as n factorial summation I runs from 1 to k, it is gi to the power of ni divided by ni factorial. If we take a log on both sides, the expression can be written as ln w is equal to ln n factorial plus summation I runs from 1 to k ni ln gi minus summation I runs from 1 to k ln ni factorial. Now we need to apply Stirling's approximation for the above equation. By applying a Stirling's approximation and further simplification, the expression looks like this. It is n ln n plus summation I runs from 1 to k ni ln gi minus summation I runs from 1 to k ni ln ni. So here, if the system must be under maximum condition, if the thermodynamic probability is the maximum, then the differentiation of ln w must be equal to 0. So hence now we differentiate the above equation. So once the differentiation is done, then the final expression for the same is, it is summation I runs from 1 to k ln gi minus ln ni dni is equal to 0. So hence the d ln w is equal to 0, then the probability is said to be maximum. The next is the distribution function. So now again let us consider we have a number of particles in a system which remains constant. Of that is equal to 0. Again the energy associated with the number of particle also remains constant. So hence the differentiation of that is equal to 0. Now we need to multiply alpha and beta for the above equations, and we need to add the two equations for the below one, that is summation I runs from 1 to n ln gi minus ln ni into dni. Now after adding all the three expressions, so we get the final expression in this form, and then we equate that to 0. The summation I runs from 1 to k dni, if we take that to the right hand side, then the final expression will look like this. It is ln gi minus ln ni plus alpha plus beta ei is equal to 0. On further simplification, f of ei is equal to, it is ni by gi, the value of this is equal to exponential alpha plus beta ei. The next is the relationship between entropy and thermodynamic probability. So here the entropy is a measure of the degree of disorder in the assembly, and S and omega are the entropy and thermodynamic probability of the system. So S is a function of thermodynamic probability, and here S is additive in nature. So hence let us consider we have two systems A and B, and the corresponding entropies are S1 and S2. So therefore, since the entropy is additive in nature, the S is equal to, it is S1 plus S2. Similarly, the probability of the combined system is, the probability is multiplicative in nature. So hence omega is equal to omega 1 and omega 2. By substituting the value of omega and S, the final expression will be written as f of omega 1 omega 2 is equal to f of omega 1 plus f of omega 2. Again we need to differentiate equation 5 keeping omega 2 as a constant with respect to omega 1, and again we need to differentiate the above equation keeping omega 2 with respect to omega 2 keeping omega 1 as a constant. On further simplification and dividing equation 6 by 7, so we get the expression as omega 2 divided by omega 1 is equal to f dash of omega 1 divided by f dash of omega 2. On further simplification and integration, the final expression for the thermodynamic probability and entropy can be written as S is equal to k ln omega plus C, where the value of C is eliminated by taking the value of omega is equal to 1 and the value of S is equal to 0. So the final expression for the entropy is S is equal to k ln omega. So this is the relationship between entropy and thermodynamic probability. The fundamental postulates of statistical mechanics. The system is composed of large number of molecules which are constantly in motion and behave like a small elastic spheres. The second postulate is all the cells in the phase space are of the equal size. And then the third one, all accessible microstate corresponding to possible macrostate are equally probable. And then the fourth one, the equilibrium state corresponds to the macro state of maximum probability. And the fifth one, conservation of matter, that is total number of the molecules in a system remains constant. And the last one is conservation of energy, the total energy of the system associated with the number of particles also remains constant. So these are the 6 postulates of statistical mechanics. Then ensemble. Ensemble is a collection of large number of microscopic particles. There are 3 types of ensembles: microcanonical ensemble, canonical ensemble, and grand canonical ensemble. A collection of essentially independent assemblies having the same energy, volume, and number of particles are called microcanonical ensemble. So these essentially independent assemblies are always separated by rigid, impermeable, and well insulated walls. So there is no exchange of matter nor energy takes place. This is similar to an isolated system where there is no exchange of energy nor the canonical ensemble. It is a collection of essentially independent assemblies having the same temperature, volume, and number of identical systems. The individual assemblies here are separated by a rigid, impermeable but diathermic walls. So this system can exchange energy but not particles. It is similar to a closed system where there is an exchange of energy takes place but not the matter. The next one is the Grand Canonical Ensemble. It is a collection of essentially independent assemblies which have temperature, volume and chemical potential same. The individual assemblies are separated by rigid, permeable and diathermic walls. In the ensemble, both exchange of energy as well as exchange of particle takes place. This is similar to a closed system in which there is an exchange of energy as well as matter. Thank you. Thank you one and all.